Hello again, this is Dr. Mike Cochrane with Value Function Analytics, and today we're going to talk about how to use a decision tree, a simple tool, to model a policy decision. In this case, modeling climate change policy. This is part one of two parts in this video series. Of the many important issues clamoring for the attention of world policymakers and government officials, perhaps global climate change is among the most controversial. Its existence, its likely effects on the environment, probable causes, and possible solutions have all been politicized to the point that many on the political left consider it the defining issue of our time, while those on the political right are highly critical of what they may perceive as junk science undergirding the assertion of anthropogenic or human-caused global warming. So one way to cut through the noise on climate change and help policymakers think clearly and rationally about governmental policies or responses rather, to the risks of global warming is to develop a model. And modeling a risk or decision scenario is a very useful way to help senior policymakers explore alternative scenarios and decision outcomes before actually taking steps to commit national resources or enter into binding treaty agreements that may have lasting economic effects. So what is a decision tree? Decision trees are valuable tools for modeling the potential outcomes of a succession of decisions and events. Each path along the tree from the origin to a terminal node describes one of potentially dozens of potential or possible outcomes. At each intermediate node of a decision tree, either one of two things are going to happen. One, a decision will be made to select one of two or more alternatives with an associated payoff value, or two, an event will occur with at least two possible random outcomes, a probabilistic event, each with an associated probability of occurrence and an associated payoff value. So here you're looking at an example of a decision tree. Decision opportunities are modeled by a square node with at least two branches, and decision alternatives can lead to either a subsequent decision or an event with a random outcome. Events are always modeled by a circular node, and each branch of an event node has an associated probability, and the probabilities of all the outcomes must sum to 1 for that event. We've constructed a climate change policy model using the basic decision tree structure, but only using probabilistic event nodes. The tree is designed to model the outcomes of a sequence of questions that are fundamental to the issue of global warming, and which must be addressed prior to proposing policy solutions. The questions are: 1. Is the Earth actually warming? A summary of modern climate history suggests that from 1979 to the present there's been a large disparity between surface thermometers, which show fairly strong warming, and independent temperature readings of satellites and balloons, which show little warming trend. And we know now that over the last 15 years, the Earth may actually not have been warming. So question number 2 is based on question number 1. If the Earth is warming, is this actually a problem? There is some disagreement over this question, with global warming activists citing the potential for rising sea levels, more extreme weather events, famines, and other catastrophes. There are a number of scientists, however, that argue that the level of future warming may actually have net beneficial effects, such as longer growing seasons, increased food production, etc. Question number 3, if the Earth is warming, and this is a problem, to what extent is human activity causing the warming? This question gets at the heart of the issue. Many environmental activists assume that human activity, that is, the burning of fossil fuels and other activities that generate carbon dioxide and other so-called greenhouse gases, is the primary cause of global warming, while others believe that warming is a natural, cyclical phenomenon primarily caused by solar cycles and the eccentricities of the Earth's axial tilt and orbit. Question 4, if human activity is the primary cause of global warming, will reducing this activity also reduce global warming? The assumption undergirding current environmental policies, such as the Kyoto Protocol, is that if anthropogenic CO2 causes warming, then reducing the output of that CO2 will retard the warming trend. Such a deterministic view of the relationship of anthropogenic CO2 and climate change is not shared by some in the scientific community, who argue that there is a high degree of uncertainty associated with understanding the effects of changes in atmospheric CO2. So finally, given all those four questions, if human activity is not the primary cause, is it still possible to stop global warming? Posing this question acknowledges the existence of it and the problem of climate change, but basically forces consideration of alternative policy solutions. Structured as a decision tree, our model might look something like this. Each of the 5 questions is modeled in the decision tree by an event node with 2 possible outcomes. There are 6 unique paths through the tree, resulting in a total of 6 outcomes. 4 of the outcomes require some type of policy response or proposed solution. And we'll look at these next. Here's the possible general policy responses to the model outcomes. And this table lists the model outcomes along with suggested high-level policy approaches or to a solution strategy. So you can see that if the model outcome is that reducing human activity fixes global warming, then current policy approaches such as cap and trade legislation, environmental regulation, these things would be the correct approaches. If it doesn't fix the problem, then we've got to be looking at solutions that are more defensive in nature, protecting low-lying areas around coastal environments and so forth. And if it's not humans that are causing it, but other means, but we still have to try to stop it, maybe we should be engaged in a massive R&D effort to produce alternative solutions to global warming. If we can't stop global warming, then we're stuck with defensive solutions again. And if global warming is not really a problem, or if the Earth is not warming, then essentially there's no response required. So there's 4 possible categories of policy response to address each of the 6 possible incomes. So the next step in the decision tree modeling process is to assign probabilities to each of the 5 events in the tree. And this normally would be best done by eliciting estimates from subject matter experts who should be able to ground their estimates in an understanding of the current state of knowledge in their field. However, the beauty of a decision model is that one can still learn a great deal about appropriate policy responses by experimenting with a range of different probabilities and observing the degree to which the outcome values are sensitive to changes in those event probabilities. Here's event 1. Now, most of the scientific community doesn't disagree that the Earth has generally been warming, so we've elected to worst case this one, and we give it like near certainty, probability of 0.9, that the Earth is warming. Note that we are going to worst case this, and we're also worst casing question number 2, which is, although there's not broad consensus regarding the degree to which the global warming will be a problem, the general thinking seems to be that it's going to be a problem, so we worst cased event number 2 as well, giving it a probability of 0.9. So here we have events 1 to 3 probabilities. We've actually also worst cased event number 3 and said the primary cause would be human activity. So the next thing, or the last 2 questions, events 4 and 5, here's where we are reflecting a certain degree of indifference or uncertainty in our model. And that is by saying that if the primary cause is human activity, we're 50% certain that reducing this activity fixes the problem. Basically, it's a 50-50 chance that it will fix or won't fix it. And if the primary cause is not human activity, which was only a probability value of 0.1, we've said that essentially we're 90% confident that we can't stop global warming. So it's basically a done deal. So these are the initial conditions for our decision tree. And here is the completed model. The completed model is put together by essentially multiplying the probabilities through each of the 6 legs of the chain, and the resulting probability distribution at the 6 triangular terminal nodes reflects the relative significance of each of the outcomes. Now, to use the products of the probabilities, we've got to assume that each of these 5 events is independent of the others, which may or may not be the case. But as the saying goes, all models are wrong and some are useful. And what we're going to do is essentially interpret those model results by looking at the probability scores. Noticing that reducing human activity does not fix the global warming problem has the same policy response as we can't stop global warming, which is the defensive solution. We would add those two together to give us a total probability score of 0.44. And then the next one, 0.36, reducing human activity fixes global warming. And then global warming not really being a problem and the Earth not warming is a probability of 0.19. And if it's possible to stop global warming by other means, it's a very low 0.01 for the massive research and development effort. But note that even with a model heavily weighted toward global warming as problematic, there's still an almost 20% chance that no response is needed. Next time, we're going to explore this model a little bit more deeply and perform a sensitivity analysis on it. So until next time, I'm Mike Cochrane at Value Function Analytics, and we'll see you then.